so chapter 11 is called Discrete Probability Distribution. Okay, so what is a distribution? A distribution is telling you, okay, what your x can take. Like say we have a variable, like something can change values. Okay, what x you can take, what value you can take, and then what probability that for that value could occur. Okay, so it's basically talking about the chance of one particular event to happen. But like a distribution is listing all of them out. You can, after you see a distribution, you can clearly tell what's the probability of each event, like the probability of that happening. So first of all, we talk about what is a discrete random variable. So a discrete random variable is a function that assigns the number of each outcomes in the sample space that in the full sample space. Thank you. What means signs a number? Okay, what means signs a number? So before, when we talk about head or tail questions, like we toss a coin for, let's say, 3 times, because that's the example we use. Okay, that's the example we use. So when we talk about head or tail, we toss it for 3 times. Then we can talk about the outcome, right? We can say this outcome we get is head, head, tail. Or the other time I got an event of tail, tail, and head. I can find the probability of that. But now I don't want to describe this outcome now. I want to give each outcome a number. After you see this number, you can know exactly what's happening. And also when I assign the number to the outcome, I don't care the order of each event happens. Okay, so for example, head, head, tail will be the same as head, tail, head. Okay, so basically you achieve the same thing, but I don't care about the order that much. So how I can assign a number to that? Can you see discrete probability distribution? Toss a coin for 3 times. Let x be the number of heads obtained. So I throw the coin for 3 times. X is a very, a number can vary because you don't know how many heads you can achieve. So first 3 times toss the coin, I can achieve like no head. Okay, that's x can be a 0. I can achieve 1 head, x can be a 1. I can achieve 2 head, x will be a 2. I can achieve 3 head, x will be a 3. So which means all head in this case. Okay, when x equals to 0, you know that your outcome will be all tails. When x equals to 1, you know there are 2 tails and 1 head in this outcome. Okay, 1 head and 2 tails in this outcome. So basically, when we talk about the numbers, I can know what the outcome is. Okay, but the order does not important. For example, I say x equals to 1. Just 1 head, 2 tail, but I don't know where is that head is happening. Okay, head can happen at the first, or second, or the third. So I can't tell the order, but I know what I achieved in the end. So let's come back to that. We have 2 types of random variable. I have, okay, so for example, this one, toss a coin for 3 times, let x be the number of head obtained. First of all, you need to know this x must be capital. Okay, it must be a capital X because only capital letters can represent a variable. Okay, something can vary. If you say a lowercase x, that means a particular value. Okay, a particular value. So must be capital X to represent random variable. So x is a random variable. So what x can be in this case? Your x can be 0, 1, 2, or 3. That is the number you're varying. Okay, that the x can vary between 0, 1, 2, and 3. Okay, it's not equal likely events. Okay, first of all, they're not equal likely. It's not the same to achieve 0, 1, 2, and 3. I'll tell you why later. But that's the x, what the value of x that x can take. So 0, 1, 2, 3 in this case. Okay. We have 2 types of random variable. One type is called discrete, and one type is called continuous. Okay, what is a discrete random variable? Discrete random variable may take on only a countable number of distinct values. Okay, so number of heads I want to achieve. It must be 0, 1, 2, and 3. Okay, countable. 4 outcomes. Okay, 4 outcomes. Another it's not necessary to be integer numbers. Okay, it's not necessary to be integer numbers. It can be any countable number. For example, the shoe size. Okay, the shoe size can be 35.5, 36, 36.5, 37. Okay, so for like shoe size for women, for example, maybe up to 42. Okay, so from 35 to 42, and I can take half size as well. So if x is like, say, I would say if x is the random variable, RV is called random variable for women's shoe size, what x could take? X could take 35, 35.5, 36, 36.5 dot 41.5 dot 42. Okay, well, it's quite a lot of number, but I can list them. I just like too lazy to list them out, but like I can list them out and I can count how many are there. Okay, this is still a discrete random variable because I can take like countable numbers. Okay, for the x, I can count it. Okay. The other one is called the continuous random variable. So what is a continuous random variable? Continuous random variable will be, for example, x is the amount of water in 600 ml bottle. Okay, x is the amount of water or the volume of water. Okay, I say maybe volume of water in the 600 ml bottle. So how many water you can have? You can have from 0 to 600, right? But any value in between is possible to take. Well, I can have 500.0009999. It's possible to achieve. It's just like I can't exactly measure that. But there is a possibility that we have that value. Okay? So any value I can take from 0 to 600. It is continuous. You can't really count them, how many values are there, because there's infinite many. I can always add one more decimal onto that. Always add one more decimal onto that. So it's countable values. Okay, it's countless values. So this is called continuous random variable. Continuous means you can take any value from a period, from a domain. So this domain is 0 to 600 because no water at all and full bottle 600 ml. So any value in between is possible. This is called continuous random variable. Normally, continuous random variable is measurement values. Okay, what is measurement values? I measure something. Okay, the length of let's say the height, the weight, okay, or like the size of something, or how long is something. Like they are measurement values. So normally these values are continuous random variable. Okay, they are continuous random variable. But there's a really special case. There's a really special case. This is a discrete, but it's a measurement value. So the volume of the water, I still take that in the bottle. Okay. Round to the nearest milliliter. Okay, the volume in the bottle, like 600 ml bottle. And I want to round the value I read to the nearest milliliter. So what I will have? I will only have 0, 1, 2, 3, 4, 5, 6 until 600 milliliters. There are 601 values. So if I round it, I'm not going to take those complex, like a lot of decimal values. What I will only take is round to nearest round to nearest milliliter. So the x I can take, I will read is only 0, 1, 2, 3, 4 until 600. So therefore, this will become a discrete random variable. It becomes countable. Okay, become countable. I can count it. Now, like, I can name what I want to have. Okay, 0, 1, 2, 3 until 600. So this is a countable value, so this is discrete. Although it's a measurement, value. Okay, so it depends on the way they describe it. First of all, like, we just talk about what is discrete and what is continuous. And follow this example here. Okay, follow this example here. First of all, I draw a tree diagram for you already on the paper. I have first trial head and tail, second trial head and tail, third trial head and tail, and I list out the probability that what it looks like, and each of that will got a 1 on 8 to happen because they are equal likely events. Okay, they are equal likely events. On each branch, that's a half of the probability. So each of them are 1 on 8. So let's have a look at. I put something in the table. Oh, sorry, change this one for me, please. Change that to lowercase x because your x is taking some value. So this is the way how you draw a table. This is a distribution. Okay, so you ask me what is the distribution, I'll tell you this is called a distribution. It lists out all the possibility for x, that is 0, 1, 2, 3, and it gives you all the probability that could happen. Okay, 1 on 8, 3 on 8, 3 on 8, and 1 on 8. This is a distribution table. Okay, this is called a distribution table. So how do I find those values? Okay, how do I find those values? First of all, is the notation. The top one is a lowercase x because that means the particular x you will take. So what x you will take? Your x can be 0, 1, 2, or 3. Okay, 0, 1, 2, or 3. The next notation here is very important. It is probability that capital X equals to lowercase x. So capital X means that's a random variable. That means your probability of that random variable equals to a particular value. In this box, that means probability x equals to 0. In that one is probability capital X equals to 1. So it is the random variable equals to a particular value. This notation, capital X equals to lowercase x, means that, okay, probability of random variable equals to a particular value. All right, how do we find 1 on 8, 3 on 8, 3 on 8, and 1 on 8? 0 means there's no head. Okay, there's no head in the 3 toes. Which one has no head? This one has no head. Okay, this one has no head. So what's the probability of that happened? It's 1 on 8. Okay, 3 tails is 1 on 8. Therefore, we have probability to achieve 0 head equals to 1 on 8. Okay, equals to 1 on 8. So similarly, we have 3 head. Well, 3 head is the situation on top. Okay, the very beginning one is 3 head. I only have that one case got 3 head. So 1 on 8 as well. Okay, 1 on 8 as well. Now, what we left is the middle 6. Okay, middle 6. Can you see the yellow one I highlight? They all got 2 head. Okay, they all got 2 head. How many cases contain 2 head? 3, right? 3 outcomes contain 2 head. What's the probability for each of that? 1 on 8. Okay, 1 on 8, 1 on 8, and 1 on 8. So what's the probability to achieve 2 head? 3 on 8. Okay, 3 times 1 on 8. There are 3 lots of that kind of case, and each of them is 1 on 8. So 3 on 8 to achieve 2 head. And similarly, the one I circled only got 1 head. Okay, 3 of those cases contain 1 head only. So again, 3 on 8 for probability to achieve 1 head. Okay, to achieve 1 head. So that's how this table has been made. Okay, so what you will do for this kind of question is make probability tables by yourself. Okay, give you some trials, like some experiment. You need to tell me What is your random variable and what's the probability to make that happen? Okay. So let's have a look. What are probability distributions? So the probability distribution of a discrete random variable x is a function px equals to probability x equals x. So this is just a notation thing. Remember I said that's the random variable x, okay, random variable x equals to a particular value. Okay, the notation will be lowercase px. Okay, that's just two different notations. So I can say probability x equals to 1, that equals to lowercase p1. They are the same. They are talking about the same thing. Assigns the probability to each value of x. It can represent, okay, what this probability distribution can be represented by. It can be represented by a rule, a table, or a graph. What we see above is a table. Okay, that's a table probability distribution. It lists out all the values of x you can take and then give you all the probabilities. Okay, so it can be a rule, can be a table, or a graph. I will talk about the other two later. Well, to say if it's a graph, I'll show you what the graph will look like. Look at above. The top is lowercase px, or I can say that's probability x equals to x, and then the bottom is x. What I will have? I will have 0, 1, 2, and 3. What I will have is, that's 1 on 8, that's 3 on 8. I can put dot on it. To have 0, I have 1 on 8. To have 1, I have 3 on 8. To have 2, I have 3 on 8. To have 3, I have 1 on 8. So that's just a, I can have dashed lines here to make sure how high is that. So this is a graph, okay? It is exactly the same as a table. Okay, I just represent dot. Okay, I represent dot on the graph. So this is a graph. And I'll talk about the function later. I'll talk about by a rule later. So you have seen how to represent the probability distribution by a table, how to represent that by a graph. Okay, that's a graph, that's a table. So the function is sometimes referred to as a mass function. Okay, discrete probability distribution can be said as a mass function. Okay, a mass function. So basically it's like how heavy is that, like that kind of thing. Okay, this feeling, like I have x equals to 0, how much weight I can have for that x equals to 0. Okay, very important thing. Okay, very important thing. This can be used for test the conditions for a discrete probability distribution. For example, I give you any distribution, like any table, okay? I just give you any table, 0, 2, 4, 6, and then probability, blah, 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 blah. Not all the tables can become a probability function, so there will be particular requirement. For example, if I say that can't become a probability distribution. Okay, I just randomly skipped something. That can't become a probability distribution. But why it can't become a probability distribution? Because, okay, you need to satisfy two conditions. First condition is all the values for each of these probability must be in between 0 to 1. You know that probability can't go over that 0 less than 1, go over that 1 less than 0. So each box, the probability needs to satisfy that. Okay, needs to satisfy that. It must be in between 0 to 1. Okay, so if I have something like that, 1.1, definitely incorrect. That's definitely not represent a probability table. Okay, it's not probability. Second, the sum of all the probability values must give you 1. As you have listed out all the outcomes for x, okay, x can be 0, 1, 2, 3. That's all the outcomes for x. So think about you sum their probability. That must give you 1 as well. Okay, you can't have like 1.1, or let's say have 0.9. Where's the other 0.1 goes? You already list out every case, so that add up should give you 1. Okay, so it needs to satisfy two requirements. One is each box, they need to have a probability in between 0 to 1. Second, you add all of these boxes together, that should give you 1. Okay, so that's what we'll have. Let's have a look at the question below here. Which of the following represents a discrete, like that's going back to what we'll have, discrete and continuous. Okay, so first of all, the number of goals scored at a football match, like what do you think that will be? Continuous or discrete? Continuous or discrete? Discrete is countable, okay, discrete. Shoe size, discrete, I have talked about that. The height of a student in mm class, continuous, is measurement value, and I'm not rounding it. Okay, the time taken to run a distance of 10 kilometers. What is it? Continuous. Time is continuous value. Okay, even though like you know you have the time, you say like 10.4 seconds, you actually can go more accurate. It's just that the machine can't work that accurate, so we only have like 0.1 decimals on the watch, but it can be more accurate in the real life. Okay, so I can take any value in between that, any value in between 0 to like 20 seconds, for example. Okay, example 2. We have a table here, okay? Lowercase x, probability x equals to x. Find the value of k for the above discrete probability distribution. Okay, it already says it's a discrete probability distribution. So it must satisfy the two requirements. One, in each box, the value needs to be in between 0 to 1. 2, you add up everything, should give you 1. You add up all the probability, that should give you 1. So you have k squared plus 0.3 minus k plus 0.3k plus 0.24 plus 0.2k plus 0.5. That should give you 1. Okay, that should give you 1. So let's solve for it. We have k squared. All right, minus k, 0.3k, 0.2k, that add together will give you minus half k. Okay, 0.5, right? 0.5 and minus 1, so it's 0.5k. And then we have 0.3, 2.54 plus 0.5 is plus 1.04 equals to 1. Correct? I think so. Okay, 0.54 plus 0.5 is 1.04, and then you have a 1 on that side. You can subtract that 1. So that becomes k squared minus half k. Well, minus 1 becomes 0.04. That's 4 over 100. That's plus 1 on 25 equals to 0. I can times 50. 50k squared minus 25k plus 2. That equals to 0. 50. 25 and 2. No, it can't work that way. 6 to 5, 5 and 10 can work. 1 and 2. Okay, that can work. 20 and 5. So 5k minus 2, 10k minus 1 equals to 0. K is 2 on 5, or k is 1 on 10. well, k equals to 0.4 or k equals to 0.1. Can I take both values? Yes or no? Why? Why no? What? I didn't hear it. Yeah. You need to test about the second condition as well. You only satisfy when you sum them equals to 1. You only satisfy one condition. You haven't checked about the second condition after you sub things in. Okay, when you sub things back, when you sub k equals to 0.4 back into this box, that is negative 0.1, right? 0.3 minus 0.4, that's negative 0.1. You can't have negative probabilities, okay? So 0.4 is incorrect. 0.4 is incorrect. And you check 0.1. Okay, 0.1 squared is good. 0.3 minus 0.1 is good. 0.3 times 0.1 plus that is good. It's not over than that. And 0.2 times 0.1, that's all good. So 0.4 is not working because when you sub that into 0.3 minus k, you have negative probability. It not satisfy the first condition. Therefore, that's wrong. Okay? So after I have 0.1, the value I have is 0.01, 0.2, 0.03, 0.27, 0.52. Okay, that's the probability. Let's have a look at the question below here. Give the following probability. X greater than 3. If it's x greater than 3, okay, what value is greater than 3 in this table? What x is greater than 3? 5, right? Only 5. So x can be negative root 3, 0, 2, and 5. So I want x greater than 3. Basically, only x equals to 5 satisfy that. So the probability will be 0.52. So probability x greater than 3, that's the same as probability x equals to 5. And that equals to 0.52. Okay, for B, probability in between 0 to 6. What value are satisfied? What value are satisfied? Can I take 0? No, it says greater than 0. You can't take 0. There's no equal signs there. I can't take 0. So only 2 and 5. Okay, so it's probability x equals to 2 plus probability x equals to 5. Okay, only 2 and 5 works. So 2 and 5 gives you 0.79. Okay, 0.79. Okay, for C, I want probability x greater or equals to 0. Given x less than 3. First of all, let's find the intersection. What the intersection will be? What do you think the intersection will be? I want greater than 0. Greater equals to 0. Intersects less than 3. What do you think the intersection will be? Greater or equals to 0. What values are greater or equals to 0? 0, 2, and 5. Okay, what value less than 3? 0, 2, and negative root 3. So what are the intersections? 0, 2. Okay, so that's probability x equals to 0 plus probability x equals to 2. That's the top. Over the probability less than 3. Less than 3 is everything except 5, right? Everything except 5. So the bottom, just 1 minus probability x equals to 5. Because I want the intersection, those two's intersection is only 0 and 2. And I will divide x less than 3. What less than 3? Everything except 5. So 1 minus probability 5. So what I will have here is 0, 2 is 0.2 plus 0.27 over 1 minus 0.52. That's 0.47 over 0.48. That equals to 47 or 48. 47 or 48. Okay, so that's this question, okay? First of all, this question teaches us how to find the k-value by adding them all equals to 1, and then I need to decide which k I can take. Which one can make every single box have a value in between 0 to 1. Second is how to evaluate those probabilities. I just have a think what value I can take from this table. Even though x is just say greater than 3, but the value I have in the equation is only 5. Okay, I have in the box is only 5. So 5 is just 0.52. That's how we find those probabilities. Okay. So the last thing I will talk about is called a probability function. Remember I said you can use a rule to represent probability mass function. Okay, we have table, graph, and the rule. Okay, that's how we do the rule. Okay, the rule says px is 1 on 8 times 18 minus 3x, where your x can only take -2, 1, 2, and 4. Okay, and ask us to find the k-value. Again, this k-value, if you add up all the probability, that should give you 1 as well. That's the same as a table. In other words, I can convert that into a table. How I can convert that into a table? So I can sketch a table. We have x and we have probability x equals to x. My x can take -2, 1, 2, and 4. When x equals to -2, okay, let's say p -2 equals to what? P -2 equals to 1 on 8. 18 minus 3 times -2. That equals to 624 over k. And we have P1. P1 is you sub 1 in, that's a 15 over k. We have P2. P2, 2, 6. 18 minus 6 is 12. 12 over k. And we have P4 is the last one. P4 is, you sub 4 in, that's a 12. It's 6 over k. Okay, those 4 values are the only values that x can take. Okay, only those 4 values that x can take. And you have the probability for each of them. And then I want to find k values. So that needs to satisfy if I add them. Should gives me 1. Okay, if I add them, that should gives me 1. So 39 plus 18, 57. That's a 57 over k equals to 1. Therefore, k equals to 57. So the value of k should be 57. Okay, that's how we find the k value. Everything will turn back into a table. Okay, everything can turn back into a table. Even though that's a function, I can still list them in a table notation. And then add up all the probabilities in the end. That should give us 1. Okay, should give us 1. And also because 6, 12, 15, 24, they're all positive values. And you divide the 57, that will still be positive values. And also 57 is greater than all of the 12, 15, 6, and 24. The value will be in between 0 to 1, definitely. Okay, definitely in between 0 to 1. So k equals to 57 will satisfy the function. It is a probability mass function. Okay, so that's how we find the k values. So in this exercise, it basically tells you how to test whether a function is a probability function or not, and what is discrete random variable and what is a continuous random variable. Next lesson, we're going to talk about something like more interesting. Okay, so it's basically talking about some distribution, some other distributions. Okay, so do some work for the first exercise, and Wednesday we'll start the next one. Okay, Wednesday we'll start the next one.